This video will teach you how to complete a process of division called synthetic division. It's another way that you can divide polynomials that's a little bit different looking than long division, but it will give you the same type of results. So we're going to look at the synthetic division process and how we can also use it to factor expressions that have more than two factors that are a result of dividing things apart. So in order to synthetically divide, basically what we are looking at are our two pieces, just kind of like a polynomial long division. We're going to take a look at our dividend once again and our divisor. Now, this has its own type of organizing that, once again, it's going to look weird the first time that you do it, but once you do it once, it's the same process over and over again. First thing we need to make sure of is, just like polynomial long division, we need to make sure we don't need any placeholders. So I look at the dividend, 3x squared plus 18x minus 32, x squared, x constant. Okay, that's in a good order. The divisor, x plus 8. Again, we've got a term with an exponent of 1, constant, we're in good shape. If you need a placeholder, you do have to use one here again so that everything does divide out correctly. Now, the way that we're going to set this up is we need to do two things. First thing here is we need to take a look at the divisor. What we need to do is figure out what the 0 would be of the divisor. So when we talk about that, all we're doing here is setting it equal to 0. In this case, x would be negative 8. Because if something is a 0, it means we can plug it in. It's going to work out beautifully within our problem. So with what we're going to do here is we're going to take that 0. We're going to take that x value, and I'm going to go ahead and put in a little elbow box. Right next to it, I'm going to put all of the numbers that we see in our dividend. So I'm going to rip off the 3, the 18, and the negative 32. Leave a little space between them so that it's not a complete jumbled mess. But we're ripping off all the coefficients and the constant. We're going to keep them in the same order, put them right next to this box. So here's how we do synthetic division. So we're going to mess with the numbers first, and I'm going to tell you what they mean. We're going to take whatever the first number is and pull it straight down, and we're going to rewrite it. I'm going to take that number, multiply it by the number that's in the box. So I'm going to do 3 times negative 8, get negative 24. I'm going to add this next column here, which gets me negative 6. I'm going to repeat the same process as I did with the last column. Take the number at the bottom of negative 6 times negative 8, and I'll get 48. Add what's in the column, we'll get a positive 16. So what do all these numbers mean? Well, when we divide this out, what essentially happens is this. So the original problem had an x squared, an x, and a constant. Okay? What ends up happening is everything is reduced by a degree of 1. So I'm going to use CON here to abbreviate constant. So we had an x squared, an x, and a constant. My results at the bottom result in an x, a constant, and my last number is always the remainder. So basically, all the numbers at the bottom row go down a degree of 1. So if I start with an x squared, my row at the bottom is going to start with an x. You'll see in a couple of problems here, I'll start with an x cubed or something else. That means we'll start with something that ends up being an x squared in that bottom row, etc. So everything goes down a degree of 1. What I'm going to do with this bottom row is simply rewrite it. The front number has an x. The second number is a constant, so there is no x with it. My last number is a remainder. So I'm going to take that remainder, put it over my divisor, like we did in polynomial long division, and I have myself an answer. So it's a weird organizer. It's kind of a weird way to divide things out, but this is essentially another way that you can divide these expressions without having to go through the polynomial process, how to go through the long division process, I should say. So we're going to see this here in the next handful of problems that I'll walk through the same steps again. But like I said, if you can do it with one problem, you can do it with all of these. Really, the most important part is understanding how do we work with the numbers at the bottom. So let's go ahead and take a look at the next problem. 4x cubed minus 8x squared plus 10 divided by x minus 6. First thing I'm going to look for is, do I need any placeholders? If I look at the dividend, I'm going to need a placeholder because there's an x cubed, an x squared, and a constant. We're missing a regular x term. So I'm going to rewrite it so that there is a regular x term. So I'm going to plug in a 0x. My divisor, x minus 6, that's good to go. We don't need to worry about that. So what I'm going to do now is I'm going to look at my divisor and say, okay, x minus 6. So you don't need to even write this part out. You should be able to do this in your head. Basically, what number can I plug in for x to make it 0? It's just going to be a 6. Make sure you're at least taking the opposite of the number that's in there, because if you don't, you're going to get some really, really wrong answers when you do this. So the x value based off the divisor is going to be 6. Once again, I'm going to put that in a little elbow box. I'm now going to look at the dividend that I rewrote and rip off all the numbers, all the coefficients, and that constant at the end. So again, if it helps, you can label at the top x cubed, x squared, x, and the constant. I'm going to go ahead and start my process by pulling down the first term, or the first number, I should say, the 4. Multiply by the number in the box, I'll get 24. Add my column, get 16. And then repeat. Take the 16 and multiply by the 6. You get 96. Add the column. You get 96. Then we'll go ahead and repeat. 96 times 6. 576. So we got some bigger numbers here. Again, just how it kind of works out. Add that last column. Get a final column here. Result of 586. So here I have all my results. Again, each of these values, so if my problem originally had an x cubed to start with, my answer will have an x squared. So we go down a degree of 1. Next term will be an x. The next term is a constant. The final term is the remainder. So I can rewrite this as 4x squared plus 16x plus 96 plus my remainder is 586 over my divisor x minus 6. And that would be my final answer using synthetic division. So again, you can check this using the long division process, as I just referenced in the last problem. You would get the same result. This is just simply another way that you can divide these problems. It's a little bit faster if you can remember the pattern for it, which you will have to do eventually on a quiz or a test. But this is another way that you can tackle these problems. Where this can come in handy is when it comes to trying to factor larger expressions apart. So we're going to take a look here at this problem here, number 3, where we've got x cubed plus 6x squared minus x minus 30. I'm asking you to factor that problem given a factor of x plus 3. You're going to do the same process we just did. So if I tell you that a factor of this gigantic expression is x plus 3, that means x plus 3 can divide into it. Now, more importantly, if it is a factor, that means it's going to divide nicely into it, meaning there's going to be no remainder. So, I don't see a need for placeholders. I'm going to look at my x plus 3 here, my divisor. The x value we're going to end up plugging in is negative 3 because we're setting it equal to 0. That's how we get that value. First thing we're going to do is go ahead and put it in my box, and I'm going to go ahead and rip off all the coefficients and constants. So I have 1, 6, negative 1, and negative 30. So again, x cubed, x squared, x, and constant. Let's repeat the process. I'm going to pull down the first number, multiply by the negative 3, add the column, and repeat. So I'll multiply, I'll add the column, multiply again. The fact that I'm telling you this is a factoring problem means if you do this synthetic division part correctly, your answer at the final column, you should get 0. So it's going to be very important, especially when you've got different signs. You see negatives pop up here all over the place. You have to make sure you are taking your time in multiplying and adding all of your columns and all that stuff correctly. So once again, we start by having a degree lower in my final row here. So what I have here in my final row is I have 1x squared, or just x squared, 3x minus 10. There is no remainder, so I don't have to write plus 0 over x plus 3 or anything like that. Okay, there is no remainder. Now, the goal of the problem is to factor it fully. Okay, so this is going to hark back to things you learned back in Unit 4A. How do we factor? And we've kind of touched on these here all throughout the last couple of chapters here. So we're going to take a look at x squared plus 3x minus 10 and factor this apart. So if it helps, do the diamond. What adds to 3 and multiplies to, this case, a times c So that'd be 1 times negative 10, 1 multiplies to negative 10. The two numbers that do that would be 5 and negative 2. Since this is what I would call the easier diamond, where you have a leading coefficient of 1 in this case, I already have the two things that I need to write my factors. So I can write my final answer with the x plus 5, the x minus 2 for my diamond. I'm then going to pull down the factor that was originally given to me, the x plus 3. This would be your final fully factored answer based off the synthetic division and then factoring what was left over when you synthetically divided. So it does combine some older processes. It does combine what you learned about factoring, and you'll see in the final example here, where the diamond will help you, and you'll use roughly the same idea. But when you do a problem that deals with factoring and you use a synthetic division process, the biggest key is that your remainder will always be 0. If you get that, then you're going to be on a great path to get a correct answer. This last problem here is the exact same idea. So I give you another long expression here, 2x cubed plus 13x squared plus 13x minus 28, given the factor x minus 1. Once again, check for placeholders. I don't need any. Look at the divisor, figure out what x should be. X would be positive 1. So we're going to go ahead and plug that in my box, and we're going to go ahead and rip off all the numbers we need. Pull down to 2. 2 times 1 is 2. Added to the 13, we get 15. 15 times 1 is 15. Added to the 13, it's 28. 28 times 1 is 28. Added to the negative 28, it's 0. That's a good thing. That means my remainder is nothing. It truly is a factor. So I can look at what's in that bottom row. Remember, we started with originally an x cubed. That means my answer here is going to have an x squared, an x, and then here's my constant of 28. So once we're here, we're going to go factor this apart because, again, the goal of the problem is let's factor. So once again, you can use your diamond, you can use guess and check, whatever works for you. So if I'm going to use the diamond, though, it's what adds to 15 and what multiplies a times c, so 2 times 28, 56. Two numbers that do that are 8 and 7. Now, the one thing you have to remember is the last problem, a little bit easier because your leading coefficient was 1. Once you fill in the diamond, you've got your factors. However, when your leading coefficient is not 1, so if it's 2, 3, 4, whatever the case may be, we have to do that fancy factoring by grouping. So unless you're, again, if you're using this strategy, you have to do the factoring by grouping. So we need to rewrite it where we keep the first term, plug in the 8 and 7 as regular x terms, and then keep the last term. Split the problem in half. Take out GCFs of each group. So you can see here I took a 2x out of the first group, take a 7 out of the second group. If you do that, you'll get the same leftovers. So what I end up with here when I factor this, I have a 2x plus 7. I have an x plus 4. So that's the result of factoring what we had left over from the synthetic division apart. Then I'm going to go ahead and pull down the x minus 1 from the original problem because that was already a factor given to us. And that gives me my fully factored final answer. So once again, synthetic division allows us to divide in a different way. Once you do the pattern once, it's the same pattern over and over again. The only thing you really need to look out for is if the problem is just saying, hey, go synthetically divide or go factor. If it's telling you to factor, again, you'll synthetically divide, but your remainder is going to be 0, which is going to allow you to factor whatever is left over a little bit further. So that's just something to keep in mind when you do these problems. So that concludes this video on how to solve polynomial problems using synthetic division.